to anchor the labeling of the positions of the elements of these sequences, I've listed 1 through 8, and then below those numbers I've indicated either a 1 or a 0. So for Bessey sequences of order 8, there are only 2 possibilities. First one, the 1s are in positions 1, 4, 6, and 7, and the 0s are in positions 2, 3, 5, 8. Or if we consider the inversion of this sequence, we get the following. The 1s are now in positions 2, 3, 5, 8, and the 0s are in positions 1, 4, 6, 7. To further aid us in understanding the diagrams on the left-hand side of the screen, I've color-coded the different digits. So if you want to picture these as a black card, a red card, a red card, black, red, black, black, red, that would work just fine as a model to represent the structure of a Bessey sequence. And here I've identified a set A as consisting of the positions 1, 4, 6, 7, and its complement, that's what the bar means, the complement of A, consisting of the positions 2, 3, 5, 8. Now what this means here, and it's also found on the top left-hand side of the screen here, so like if you can see the hand moving on the left, in each corner I have a little diagram. So this first one, what it's denoting is the objects in these positions, 1, 4, 6, 7, after they've been rearranged or shuffled, will still be in positions 1, 4, 6, 7, even though they may have traded places within these 4 position values. The same thing here. This depiction represents the objects in position 2, 3, 5, 8 as staying in those positions, 2, 3, 5, 8, even though they may switch places within this list of position values. Now that's in contrast to the following, where we have the objects in these position values. After the shuffle, they get moved to the positions that are found in a complement, namely 2, 3, 5, 8. So in other words, there's a wholesale exchange of the 1, 4, 6, 7 with some assignment of 2, 3, 5, 8. It's like they just switch places. For example, if the reds and blacks all switch places here, that would mean that in the first position it would now be a red card, namely one of the ones that initially started out in position 2, 3, 5, 8. The next one would be black, and then black, red, red, black. Okay, so let's go a bit more deeply into the mathematics. So if you focus here on the left, we're going to look at what is called the LR shuffle. That's shuffling into a left and right pile, in which we will stack the left pile on top of the right. And it leads to this permutation. Okay, so we're going to talk about permutations and notation for permutations. Okay, so to figure out what permutation is associated with this shuffle, what we do is we begin with cards clearly labeled 1 through 8. These numerals are really just marking the original position of these cards. That's the whole reason for the numerals. Okay, so that's where we're starting. 1, 2, 3, 4, 5, 6, 7, 8. Okay, now what you do to find the permutation associated with that shuffle is you turn the cards over and you perform the shuffle. So we're going to do a left-right with stacking left pile on top of the right. Very good. That is the shuffle. What is the new ordering brought about because of that shuffle? Well, let's take a look. Okay, let me just put this down so you can see it. So it's 7, 5, 3, 1, 8, 6, 4, 2. Okay, so what I've done here is I've simply written down the new ordering. 7, 5, 3, 1, 8, 6, 4, 2. And this is called Cauchy's two-line notation. It's a way of representing permutations. It's a way of representing the result of this shuffle on this packet of 8 cards. Now this isn't what we have up here. We have something far more compact. So what we do is we change this 2-line notation into something called cycle notation. So this is far more compressed and succinct. So the way that I got the 174 up here, so you just read it off here. So we see that 1, so what was in position 1 gets replaced by what was in position 7, right? So 1 goes to 7. So we say 1 goes to 7. Where does 7 go? 7 over here. We're looking at the top row. 7 goes to 4. Very good. Where does 4 go? Well, 4 goes to 1. Well, guess what? That wraps around. So a way to compress all of that information into as few characters as possible is the following. We start with an open left parenthesis, and then we just write the value 1, 7, 4, and then close with a right parenthesis, where the assumption here is the 4 wraps around to the first value in that cycle, namely 1. So the information here is capturing what's happening with 3 of the elements in our original sequence. Okay, now let's take a look at some more here. So 2 goes to 5, so there's an arrow there. Where does 5 go? 5 goes to 8, so I've written an 8 to the right. Where does 8 go? 8 goes to 2, and 2 is where we started, so it wraps around. So all of this information here can be consolidated into just these symbols here. Now what is happening with the others? So look at 3. Ooh, that's interesting, and you can see it. So remember, this is the top card. So this is position 1, 2, 3. Oh, the card in position 3 stayed in position 3. So that's why we have an arrow from 3 to 3, and we write it as a single cycle. It's called a fixed point. So if you perform this shuffle 1 time or 1,000,000 times, 3 stays right where it started. It doesn't go anywhere. It's a fixed point. The same thing happens with whatever was originally in position 6. This is position 6. It didn't go anywhere. It stayed right where it is. Despite all the movement of those cards, as we're shuffling it, the cards in position 3 and 6 arrived back where they started. They did not get moved to a new position in the end. Now, ordinarily, these 1 cycles, we call them, are not necessarily included in the cycle representation of the permutation, provided that the context is clear regarding the size of the set you're working with. So as long as we're clear on the fact that we're looking at 8 objects, we can safely drop these. And because a 3 is not present, it's assumed to be a fixed point, which it is. And because a 6 is not present anywhere in these parentheses, it's assumed to be a fixed point, which it is. Now if we color code these, which gets us closer to reading the diagrams on the left, the cycle notation for this permutation would look like this. Remember, 1, 4, 6, 7, we color-coded them black. 2, 3, 5, 8 are color-coded red. And I've included the single cycles just so that we can see the following. Each value gets sent to a value of the same color. So what I thought we would do is go ahead and draw by hand the first shuffle diagram on the top left up over here. We'll do just one of these by hand just so you can see how it's constructed. Okay, so for this shuffle, the left-right shuffle, on which we stack the left pile on top of the right, as just illustrated, leads to the following permutation. So 1 gets sent to 7. Okay, so what you do here is you start at 1, 1's right there, and you draw an arrow for 1 to 7. So I'll just draw an arrow from 1 to 7. And the direction is as follows. We're going from 1 to 7. So 1 to 7, 7 to 4. And in just a moment, I'll give you some additional ways of interpreting this 7 goes to 4. What does that really mean? Okay, so we'll give you some practical ways to make sense of that statement. Going back to our cycle notation, 4 wraps around and gets sent to 1. So that means we just draw a line straight up. And it would go with an arrow pointing upward because it's 4 goes to 1. So now we have to look at the second term in our permutation. So 2, 5, 8. Okay, so 2 gets sent to 5. So I'll draw a line, a directed line, an arrow, from 2 to 5. Just like that. And then 5 goes to 8. Okay, so it just goes straight up, just like this. Okay, and then 8 wraps around and goes to 2. So 8 goes to 2. Okay, so we draw a line from 8 to 2 with an arrow pointing towards 2. And then something else interesting happens because 3 is not present, and we already know that it's a fixed point. What that means then is you can just draw it with no markings at all as far as an arrow, which is what's done on the computer-drawn version up there. You can also do this, which is just fine, where it's indicating that 3 is sent to 3. 6 is sent to 6. So they don't move anywhere. They're fixed points. And then let's take a look at what's happening with set A. Remember, the set A consists of the values 1, 4, 6, 7. Well, what's found in positions 1, 4, 6, 7 either stay where they are in the case of 6, or they get assigned to one of the other values in that set, 1, 4, 6, 7. So we would say that A gets sent to A. Well, once we know that, then we also know that A complement, which are the red vertices there, red points, so 2, 5, 8, and 3, those get sent somewhere to themselves. Either they're fixed, as in the case of 3, or they just get moved around, permuted among themselves, at 2, 5, 8. So in this case, we would say that this shuffle preserves Bessey sequences of order 8. Okay, now in a minute we're going to do another shuffle where it inverts it. It sends A to A complement and A complement to A. Now that will pose no difficulties for us moving forward. That is perfectly acceptable for that to happen. It will not undermine anything we hope to do. So I thought I would give you kind of a metaphor or narrative to make sense of the colored dots on our diagram and the arrows pointing in certain directions. So what I want you to do is picture, if you've seen Monty Python's spoof involving I think it's maybe a 100-meter dash, where you have these ancient figures, Archimedes and Karl Marx and other philosophers running, seeing who can run the fastest. Okay, so it's just a silly little Monty Python spoof. Okay, so these are their starting positions. So this guy here, William the First, starts in the first position. Edward Elder in the second, and then we have third, fourth, fifth, sixth, and then all the way to Ethelred in the 8th position. Okay, so what we want to do is we're going to have them run this 100-meter dash, and then we'll see how each of them did at the end. Now the way that we'll get the new ordering for these runners is we'll just perform this shuffle that we've just done. The LR with left stacked on right. Okay, so I'll do left, right, left, right, left, right, left, right, stack left on right. Okay, that's the shuffle we've been doing. Okay, now we know what order is going to come out because we've seen it already, right? So we're going to get, of course, 7 will be first, then 5, 3, ace or 1, 8, 6, 4, and then a 2. Okay, so that agrees with what we did earlier. Now the way to think about these is when we're looking at the diagram here that we've just drawn, is think about it in this way. First, so the race has been completed. Okay, they've run, and this is this is the first person to cross the finish line, second, third, all the way up to the last person, the loser over here, last person to cross the finish line. Okay, so what does this mean? This means that first place goes to the individual who was originally in 7th place, right? Because we had them ace through 8 originally. 7th place, over here, this is 7th place, goes to whoever was originally in the 4th position. And that's what we see here. 4th place, which is over here, goes to the individual who was originally in position 1. And that is the person, William I, was originally in position 1. Okay? So this is a way of interpreting really what's going on. So we say first place goes to whoever started in the 7th position. So the arrow going from 1 to 7 is best interpreted in that sort of way. And second place goes to whoever started in the 5th position. So is that true? Second place goes to the person who originally started in the 5th position. That's true. We see it right here. The second place winner is now the 5 of hearts. And that 5 of hearts started in the 5th position. Okay? So you can think of these as assigning a new placement order to the cards after the shuffle has been completed. So that's a way to interpret these permutations written in cycle notation or as a shuffle diagram, as depicted here. So I'm hoping that explains how it is I got this diagram here on the left for the permutation that results from performing this particular shuffle. And as some specialized vocabulary, we say that 2, 5, 8 are in the same orbit. Orbit. So that's a technical word from group theory. So one orbit is the set consisting of 2, 5, 8. Okay. Oops, sorry about that. So that's one orbit. I'll say orbits. Another orbit is one consisting of just 3 because it doesn't go anywhere. And then 2 other orbits, I'll go ahead and just do them in black because we have them color-coded in black, will be 1, 7, 4. So it's like they just cycle around. They just trade places sequentially there. So 1, 4, 7. I've just listed them in order, which doesn't matter when you're writing set notation. And then the remaining orbit is the one over here for 6. 6 is in its own little orbit, since this shuffle leaves 6 alone. And the important thing to understand regarding Bessey sequences is that all of the red values after the shuffle will stay within positions marked by the red values, and the same thing for the black values here. After the shuffle, they'll stay in positions that are marked black, namely 1, 4, 6, 7. So to quickly give a fun little application of all of this, so I have this arrangement of the kings and queens, and really anyone looking at this would almost certainly not see anything of consequence. They wouldn't look at that and go, oh, that has a special structure to it. It doesn't seem to have anything to it. Now, you knowing what Bessey sequences are, just taking a moment or two, you'll recognize that this is a Bessey sequence relative to kings and queens. Well, that being the case means that we can perform the shuffle that we've just been using, the left-right, with stacking left on right to this packet of cards, and it will return it to its original structure type. Okay, so here we are. We're back to a queen on top, which is what we had at the beginning, and then a couple of kings, then a queen. Okay, so this is like 1, 0, 0, 1, and then 0, 1, 1, 0. Okay, so how would that help us? Okay, well, if you just hold the cards face down. We know for one thing that the top card is a queen, okay? So what we know then is there's a queen, a king, king, queen, king, queen, queen, king, okay? Just because of the assignments. So that means I know that this is a queen, the next two are kings, this one's a queen, this one's a king, the next two are queens, the last one's a king, okay? And so I could have performed that left-right shuffle with left on right. I could have done one of those or 5,000 of those, whatever the spectator asked for. And then after doing all of that, I could separate these 8 cards into 2 piles, one consisting of the queens and one consisting of the kings. Moreover, I would know which is which. And isn't that amazing? So I could say, well, you know, we did all that mixing. Let's say we did that shuffle 7 times, and that's what the spectator asked for. And then I did this, 1 0 0 1 0 1 1 0 to deal them down, to separate the queens from the kings. And then I could come over here and say, wow, as I was dealing those down kind of in a random fashion, it just felt like certain cards should go left or right. And that's all I did. I just kind of felt just a little push in a certain direction to put each card on the left or on the right. Okay, and I think I put 4 cards in each. I wonder what I put in each one of these. Well, that's weird. These feel like they're all the same. There's no way. These are all the same value? Well, they are. Are they kings or queens? Ooh, I think, these are the queens. I can just tell. Queens have a different aura and resonance than kings do. I think these are the 4 queens. What are the chances that I just happen to separate all of the queens into one pile? Oh, I can't believe it. I just put them down left, right, according to just little subtle impressions I had as I was dealing those. Isn't that amazing? I wonder if I could do that again. And of course you can do it as many times as you like, forever, because of the mathematics, right? Okay. So anyway, that's just kind of a simple example of how you could use what we've shown you thus far. Okay, so let's take a look at these other permutations.